Good morning and welcome to Monday of week 6 of your Physics 5 a day. And today we're starting medical. So we're going to begin by reminding ourselves about alpha, beta and gamma radiation. Remember from GCSE that alpha particles are not very penetrating at all. They'll be stopped by skin or paper, whereas gamma rays are very penetrating. They can pass through most materials, and it takes a few meters of concrete or a few centimeters of lead, which is extremely dense, to stop gamma rays. Okay, so gamma rays, very penetrating. Also important is how ionizing they are. So alpha particles are very ionizing. They're so big, basically, that they as they try and pass through a material, they're knocking electrons off everywhere they go. So they're extremely ionizing. Whereas gamma rays are not very ionizing at all because they basically sail straight through. The chances of them being absorbed by an electron as they're passing through a material are very low. So gamma rays, they are ionizing radiation, but the chances of them ionizing atoms on their way through you is low. Okay, that's relevant because we are about to discuss tracers. And the most common tracer used in the whole world is this one here, technetium-99m. So this is a radioactive material, a radioactive isotope, and it emits gamma rays. Okay, so what happens when you are using a tracer is that your patient ingests the gamma emitter. Now, you might think, doesn't sound like a great idea. There are risks, but you would only use it if the benefits were going to outweigh the risks. And the risks are very low because, as we said before, the gamma rays are not very penetrating. So if you use a very weak dose, then the risks are low. The chances that the gamma rays are going to ionize anything on the way out your body is low enough that it is unlikely to give you any cancer at all. Okay, so that's one thing. And one example of when you use technetium-99m is when you're looking at, say, bone growth. And basically what happens is that the different cells in your body absorb different chemicals and different molecules at different rates. So osteoblast cells in your bones preferentially take up this. So that means they take up more of this than other cells do. So what that means is that if you swallow a whole load of technetium-99, you're going to find that more of it ends up in your bones. Okay, from there, so let's just say, I'm going to draw this. That's meant to be the skeleton there. So more technetium-99 ends up in your bones. Okay, and then when it starts decay, well, it's going to decay all the time, but when it decays, you're going to find that you have more gamma rays coming out of your bones than you do out of your other cells. And what this does is it allows you to see whether you've got bones growing where they shouldn't or bones growing more than they should. And it sort of lets you look for fractures and things like that. Rather than looking at bones, though, if you were interested in looking at brain activity or looking for cancerous growths, then what you're interested in is very hungry cells. So cells that are taking in a lot more glucose than other cells. And so then what you do is you take some other kind of weak gamma emitter, which when you're talking about medical, is referred to as a radioisotope. So you take that one and you attach it to glucose. I've no idea how you attach it to glucose, but they do. And then what you've made is called a radiopharmaceutical. So now you've got a gamma emitter attached to something that's going to be taken up a lot more by tumours or by active parts of the brain. And so then it's going to be tumours or active parts of the brain that are giving out a lot more gamma radiation than other parts of the body, again allowing you to image that part of the body. Okay, so to summarise so far, your patient ingests a gamma emitter that you have chosen because it's going to collect in a particular kind of cell that you're trying to look at. and that means that from those cells, more gamma rays are going to be emitted, and then you need to detect those gamma rays. Okay, so that's what we're going to look at now. Okay, but the gamma radiation coming off the patient, remember, is very weak. So how do we detect it and turn it into an image? Well, the first thing that happens is that this gamma ray here this one is exactly parallel to one of these very narrow tubes. So this gamma ray is going to be able to travel along this tube, but another one that was at a slightly different angle wouldn't be able to travel along the tubes. And so this array of parallel narrow tubes is called a collimator. And what it means is you know the direction that those gamma rays came from. Okay, so the gamma ray travels along here, and then when it gets to this next stage, this is called the scintillator. So the gamma ray travels along here, and then when it gets to the scintillator, it excites an atom. So one of the electrons in the atom absorbs the gamma photon and jumps up to a higher energy level. But then when it falls back down, it's got many smaller energy gaps that it can fall down. So whereas it has absorbed one gamma photon, what it's going to emit is many visible photons, visible light photons. So that's good. We've gone from one photon to lots of photons. So that's a help. Now, when all of these photons get to the next stage, which is called the photomultiplier tubes, I think this is a little bit misleading because it makes it sound like we're going to have more photons. We're not. We're going to get lots of electrons. So all the photons come in, and each photon is going to cause an electron to escape its atom, and that's going to cause a little bit of a current. But what the photomultiplier tube does is that it then amplifies that. So that then you have a much bigger current. And then that is what's sent down to the computer, and the computer turns it into the image. Okay, so to summarize, the point of the collimator is to make sure that only photons parallel to the tubes pass through, and that means that we can know where those gamma photons came from. Remember, we're trying to work out where they came from. The scintillator causes one gamma photon to turn into many visible light photons, and that's good because we're trying to turn a weak signal into something more easy to register. And then each visible photon causes an electron to be emitted in the photomultiplier tubes. This is causing a small current, and the photomultiplier tubes amplify it into a much bigger current. And then finally, this bigger current is sent down to the computer, and it does that for each one of these tubes, so it can work out where those gamma rays were emitted from. And the last point to make here is about the collimator and resolution. So, if you have very thin, long tubes in your collimator, then what that means is, let's just take this one at the top here, that because we said we want them going as parallel as possible. Well, I could get, if a gamma ray came off like that, that would get through the tube, and then at the other extreme, if I had a gamma photon in that direction, that would get through the tube as well. And so we can see that what I would consider to be the same point is actually about that much on the patient. Whereas if I have thicker, shorter tubes, I know I've exaggerated massively here, but here I could have this gamma photon is still actually going to get through that top tube there, and so is this one. And so you can see that what I would consider to be coming from the same point there is a massive area of the patient, relatively speaking. So this has a better resolution. On this one, it's like having a picture made of pixels this big. And this one is going to be like having a picture made of pixels that big. So this one's going to give us a much higher resolution image. Okay, so here is a tracer question that first of all takes in It puts in a bit of nuclear there as well. Okay, so activity is the number of decays per second. Okay, and then next, we know that we've got an initial activity of 500 megabecquerels. So that means that 500 million photons per second are being emitted. And if each one has that energy, then that's going to give us this many joules per second. And lastly, here's the bit about the gamma camera. Name and describe the functions of the main components of the gamma camera. Okay, so you get 1 mark for saying there's a collimator, and that is to make sure that the gamma photons are travelling parallel to the tubes. Then you've got the scintillator, which takes 1 gamma photon and turns it into many visible light photons for the 2nd mark. For the 3rd mark, then those go into photomultiplier tubes, which takes a visible light photon and turns it into many electrons. And then for the 4th mark, though that current is passed into a computer where an image is formed. And the 5th mark is for saying that the quality of the image is improved by having narrower or thinner or longer tubes in the collimator.